Okay, let's pick up where we left off. We were looking last time at how the range does not take into account what's happening in the middle of our distributions. So we want another statistic that will help us take into account the middle of our distributions. So that statistic is sum of squares. Sum of squares is a measure of variability that does consider every score. All right, so let's take a look at how that happens with sum of squares. All right, so again, I'm going to use just a really small data set. I'm going to bring that one back from earlier. So x is just a variable. You'll have to kind of get used to me doing that. If it helps you to put it in a context, please do. So if x, you wanted to call it shoe size or reading level or anything, whatever that is, it has to be intervally scaled. So it needs to be some sort of score. All right, and the first thing we're going to do is figure out how far every score is from the mean. So if x is your score, we're going to see how far it is from our mean. And this is called the deviation score. Deviation score, because it's how far it deviates from the mean. Okay, you might remember the deviation score from your homework. All right, so we're going to do, first of all, we have to find the mean, don't we? What is the mean of that? Do you remember? It was 3, right? Okay, so let's do 1 minus 3, 2 minus 3, 3 minus 3, 4 minus 3, 5 minus 3, minus 3. So let's see what that equals. All right, we've got -2, -1, -1, 0, 1, 2. All right, so these are our deviation scores. If we summed our deviation scores, what should we always get? 0, right? And it's another indication that the mean is the balance point of the distribution, because now all of our scores are balanced around this mean. So when I subtract the mean, I should get 0. Then what's on one side of the mean, which is my 1 and my 2, should balance what's on my other side of my mean, which is 4 and 5. So if I sum those deviation scores, I should get 0. All right? But for this, we're looking at sum of squares. So we want to do what it sounds like. We want to, again, get our deviation scores, but now we want to square them. All right? So 2 times 2 is 2, or -2 times -2 is 2. 1, 0, 1, and 2 times 2 is 4, right? Yeah, and that is 4. I'm sorry. 2 times 2 is 4. Okay, so now we add 4, 5, 6, and 4 is 10. So sum of squares equals 10. Or you might see it also written sum of squares like SOS, which might be more fitting if you feel a little bit lost. You might want to write SOS. But the sum of squares is simply a measure of how spread out our scores are, or how variable our scores are. Okay? It doesn't have, say, a minimum and a maximum or some bounds it can fit in. It just gets bigger if your scores over here, if these scores become more spread out, sum of squares will get bigger. If they become more condensed or less spread out, then sum of squares will get smaller. And that's pretty much all we can say about sum of squares. But it tells us how spread out all the scores are, and it gives us information about individual differences. And this is what I was saying a second ago. As individual differences increase, sum of squares will increase. Okay, so let's look at another example of that. So I'm going to draw a distribution up here using some shapes. And so we have 25, 35, 45, 55, 65. Actually, let's let's back that down a little bit. What if we do 25, 35, or actually let's do 30, 25, 30, 35, just trying to make it easy on us, 40, and 40, oops, 45. I'm using one of these touchpads, but the bad thing is if you rest your hand on it like you might a sheet of paper, it starts to mess with everything else. So I'm kind of having to hold my hand up while I write, so I apologize. What if I started with a distribution that looks like this? I have some squares. These are supposed to be squares. I have two 30s, three 35s, and two 40s. Okay, so just for a little more practice, let's go ahead and calculate the sum of squares for that. So I have 30, 30, 35, 35, 35, and 40. All right, so remember, first step is how far each score is from the mean. And then we're going to take that, how far that deviation score, and then we're going to square it. Okay, so first step, we have to find the mean, and you can calculate the mean, or you can use our drawing up here to help you figure out the balance point. The balance point here is going to be 35. Okay, that's where the distribution is balanced on either side, so the mean is 35. So I'm going to subtract 35 each time. And I'll try to subtract correctly this time. Okay, oops, 35. All right, so we have what? -5, -5, 0, 0, 0, and 5. Okay, so now we're going to square those. -5 times -5 is positive 25. And then 0, 0, 0, and positive 25. All right, oops, we had two 40s, didn't we? You guys, I know if we were in class, you could bring those to my attention. We had another 40, which would be another 25. All right, so that sum of squares is equal to 100. You see how we got that? Okay. So that sum of squares is equal to 100. Okay, so 100 is an indication of how spread out these scores are. All right, we took into account every score. What are scores at the mean contributing to our sum of squares? Can you see that they're contributing nothing? So they're not contributing to the spread of the scores, which if you think about it, that makes sense. Because if you're adding scores here in the middle at the mean, your scores are not becoming more spread out, are they? They are just kind of being stacked up there. So as a measure of spread outness, adding scores at the mean doesn't affect anything. All right? But let's look, what if we added a couple of scores and we added them, there it is. We added them over here. We added 125 and 145. All right, so now I'm just going to continue my list over here. So now I have another X, another score, which is going to be 25, and I have another one, which is 45. All right. So before I calculate the deviation score, I have to think, all right, did those affect the mean at all? Or is 35 still that balance point? Yeah, it is still that balance point. So I'm going to subtract 35 from both of these. All right, and now what do I get here? 25 minus 35, -10, and then positive 10. And then if I square those, which is this next part, right? Then I'll get 100 and 100. So if I take my previous sum of squares and add my new amounts, my new total sum of squares is 300. All right, can you see that? So this illustration was to help you see that sum of squares of 100 kind of is what it is. It's a measure of how spread our initial squares were. When we added our triangles, if you can look, our data, if we had drawn a curve before and then after, our data is a little more spread out now, which we can see numerically as our sum of squares increased. It went from 100 to 300. So there's no, sum of squares doesn't range from one amount to another. It doesn't have a minimum and a maximum. But as your data becomes more spread out, sum of squares will increase. Okay? So we're going to skip over this little question in the next slide and go right on to our problem. So the problem is, what if we want to compare variability of two or more groups? All right. That is a problem with sum of squares. So let's look at an example of what I mean by that. Let me click back on my pen. Okay, so let's look at that example. So we have group A, which will be 4, 5, 6, 4, 5, 6. So 4, 5, 6. And we have 1, 4, and 1, 6, and we have 4 5s. I did that not right. Let's get my slide down a little bit. Sorry, thank you for bearing with me. That's not what I wanted to do. Okay. All right, there we go. Now, so there's my first distribution right there. And then comparing it to group B, that looks similar. You still have 4, 5, 6. And we have 1 here, 2 5s, and 1 6. All right, so if I'm thinking about sum of squares, if I work through this, and I would encourage you to work through both of these, but if I'm looking only at sum of squares, if I were to calculate sum of squares, and again, go ahead and do it on, maybe pause the video and figure it out, but sum of squares is going to be 2 for both cases. All right, so sum of squares, again, as a measure of spread outness, is telling us that this distribution here is the same as this distribution here. But you can tell that if I'm looking, even if I draw just a little sketch of my curves here, that this situation is not as spread out. It has a stronger central tendency, the 5 as the mean. These both have a mean of 5, right? For thinking balance point. So this has a mean of 5. Okay, so this has a stronger central tendency in that the 5 is a better representation of all the numbers than it is down here. Spread outness, sum of squares would have us to believe that these distributions are identical, when obviously they're not. 5 looks different, or A looks different than B. So the problem with sum of squares is it's not taken into account what? All right, your sample size. So your N. Sample size. Sample size is being ignored, right? Because when we add scores at the mean, what does it contribute to sum of squares? Nothing, but it is contributing to the spread of our distribution. It's making us either less spread out or more spread out if we have fewer scores at the mean. Okay, so we do have a solution for that, and that is going to be variance. I'm going to stop here and pick up again so these don't get too long.